Hello everyone, welcome back. So now it's time to actually try out an example with tipping or slipping. We gotta figure out, because all we ask is what is the maximum force P that can be applied without causing movement of the crate. That's either rotation or translation. So what's the plan? I'm not gonna give you one. I'm kidding. Here you go. So first off, draw a free body diagram of the box, determine your unknowns, make your assumptions, make sure they're good. And apply your equations of equilibrium to solve what you don't know. And check. X has to be somewhere inside of the box. Frictional force can't be more than the max frictional force. So if you assumed one and you were wrong, you'll see it there. So once again, as always, I'm going to count to 3, and when I finish, you're going to come back, you're going to show off what you've done, and hopefully everything's gone well for you. So 1, 2, 3. Okay, you're back. Let's try out this example together now. So first off, let's draw a free body diagram. Okay, I've got my force. I know how high it's applied. I know the weight's applied at the center of gravity. I've got this nice little line right down to the center. I know the normal force is applied somewhere, as is the frictional force. If you're wondering, well, why isn't the frictional force, why isn't it shown over here? It doesn't actually matter where it's applied because it's in line with this point. And so we really just need to figure out what X, N, and F are and P. That's 4 unknowns. We only have 3 equilibrium equations. And you're like, well, wait, we know what the normal force is because it's just equal to the weight. That's one of your equilibrium equations. That was some of the forces in the y direction. So don't confuse yourself by thinking you can get away with it. You'll quickly find that you can. Just don't start off by getting confused. Okay, so let's make an assumption. So let's assume that the crate slips. Okay, if the crate slips, that means that our force F is the max frictional force. And we'll need to figure out where this normal force would be applied to maintain equilibrium. Because we're not saying that it is slipping, we're trying to figure stuff out then. We're just saying it would slip if I applied an eensy-weensy bit more force on that crate. Okay, so our frictional force equation is going to be the coefficient of friction, which is 0.4, times the normal force, and that comes out to be 0.4 newtons. Or sorry, 0.4 times the normal force. That's why it's difficult when they reuse letters. So we go back to this. We have to make these decisions. We start using our equilibrium equation. So some of the forces in the x direction will P, and that'll be 0.4 times the normal force because this is our friction force right here. Some of the force in the y direction, we have our normal force and 250 newtons. That's 2 equations, 2 unknowns I can solve. So it comes out that P will be 100 pounds and the normal force will be 250 pounds. We know the normal force is right, but is the pressure right? Sorry, not the pressure, the load correct? Well, is this more than our max frictional force, 0.4 times the normal force? And so we have to check. Let's see. Actually, we don't have to check. I'm sorry, I'm getting enough today. That's already taken into account here. We have to check if it's going to slip or tip first. So if this isn't going to tip, then this normal force must be applied somewhere in this distance. And so we have to do our last equilibrium equation to solve for x. Now sadly, x is 1.8. You solve this equation, it comes up to 1.8, which means your normal force would need to be applied somewhere over here. Which, you could put a little slat on the bottom of this box, but that wasn't shown, and so x can't be over there. And therefore, this is not going to slip. It will tip based on these forces. So I retry everything. I'm going to recorrect my free body diagram. So my pressure, my load, here, is still in the same place. My weight's in the same place. My normal force and friction are both applied at this bottom right corner. And then I can solve all my equations again. So normal force is still going to be 250 pounds. The load is going to be equal to the frictional force, which is like, ooh, how am I going to solve for that? Well, let's look and see. And then finally, I can take the sum of the moments around a particular point to get my last equation. So with this, I'm going to take the sum of the moments around this point right here. I only have 2 components, one from the normal force and one from the load that actually have a component that will be causing a moment around that point. I solve and I get that P is equal to 83.3 pounds. And that will tell us that, well, F must also be 83.3 pounds. And this is good because this actually works out. Because this will be less than my max frictional force. If it was more, then something has gone terribly wrong with this setup. You shouldn't run into any problems that like trick you and say, you can't slip or tip. This is a broken problem. If that's the case, it's on me. And I'll give you extra credit if you point out to me. So, hopefully this helps you get an idea of how you're supposed to solve these problems. We make an assumption. We say it's going to slip, or we say it's going to tip. And using that assumption, we solve for everything else and check to see if it makes sense. In this case, it makes sense because our max frictional force is more than the actual frictional force. So it works. So I hope this helps you, and we'll do another problem next time. Have a wonderful day. Bye-bye.